Making measurements is an essential part of physics. Whether it is a physics student performing a lab or physicists doing vital research, the discovery of all laws in science, no matter when they were made, involved countless measurements. In today's program, you will learn the proper and scientifically honest way to make measurements and use them in calculations. During this lesson, you will distinguish between accuracy and precision of measurements, make measurements in the lab using only significant digits, and determine the number of significant digits in measurements.
I know you've been wondering when you would actually get to do some things in the lab. Well, today is the day. You'll be making some measurements and doing some calculations. And you'll even be racing the paper frogs that you made on the first or second day of school. But before you get started, there are some things we need to review about measurements. No matter who is making a measurement or what instrument is being used, no measurement is completely certain. It is important for scientists, as well as physics students, to know how much you can trust your measurements. In this course, we are going to express the uncertainty of measurements in two ways: accuracy and precision.
The first way of expressing the uncertainty of a measurement is accuracy. Accuracy is the closeness of a measurement to the accepted value. The accepted values of fundamental quantities are called standards. Let's look at an example of accuracy. Carl and Mary are determining the boiling point of water. Carl finds it to be 109 degrees Celsius, and Mary finds it to be 99 degrees Celsius. We know that the accepted value for the boiling point of water is 100 degrees Celsius. Which measurement is more accurate?
Of course, Mary's measurement of 99 degrees Celsius is more accurate, since it is closer to the accepted value. But did Carl do bad lab work? Maybe not. Sometimes the instruments we use in a high school physics lab are inaccurate. Thermometers are often at fault. Your local teacher will take minor inaccuracies with your classroom thermometers into consideration. But you can't simply blame the thermometer if you misread an instrument or make a mistake in calculations. If your results are way off from the true value, that's another problem.
The second way we express the uncertainty of a measurement is precision. Precision describes the reproducibility of a measurement. Will the same instrument give the same measurement over and over, no matter who uses it?
Let's get back to Carl and his thermometer. Suppose that not only did Carl get 109 degrees Celsius when he measured the temperature of boiling water, but his lab partner also measured the boiling point as 109 degrees Celsius. When both students asked their teacher for help, she too measured the temperature of the boiling water as 109 degrees Celsius. Was Carl's measurement reproducible? Did the three measurements with the same instrument agree with each other? The answer to both questions is yes. So the measurements are precise, even if they are not very accurate.
Look at this data. The same experiment was performed 4 times to find the speed of sound in air at a certain temperature. Are the measurements precise? If you said no, you're right. The measurements don't agree with each other, so they are not reproducible. Because the measurements are all different, the student decides to calculate the average of all the trials by adding them all and dividing by 4. What does she find? The average value for the speed of sound is 336 meters per second. This is a measured or experimental value.
Well. Looks like our student had some blind luck on this experiment. The actual value of the speed of sound at the temperature in the lab is 335 meters per second. So, even though her measurements were not precise, the average value is pretty accurate. Sometimes that happens, but it is usually just a lucky coincidence. When measuring techniques and instruments are not precise, it's difficult to be accurate.
Look at these 4 targets. Each has 6 holes, showing where the 6 shots have hit the target. Sketch these in your notes, and for each, choose good or poor to describe the precision and average accuracy of the shots. In picture A, the marks are close together, so precision is good. But the average would be off the target, so average accuracy is poor. In picture B, the precision is very poor. You could not predict with any confidence where the next shot would hit. But by luck, if you averaged, you would see that the up-down and left-right errors would cancel, so average accuracy would be good. In C, both precision and accuracy are good. In D, both precision and accuracy are poor. The average of all the shots would still be off to the left.
Were you tricked by the marks on target B? The word that made the difference was average. Watch out for it, and you won't get fooled again.
One way to show the precision of a measurement is to use significant digits. Significant digits are all measured digits plus one estimated digit. When you make a measurement in the lab, read the smallest division on the instrument and then estimate one more digit. Don't forget to estimate the last digit. Here's an example. Most people would agree that the edge of the object is at least at the 3.2 centimeter mark. Bob might say that the edge falls exactly on the 2/10 mark. He would record the length as 3.20 centimeters. The 0 is the estimated digit. Tasha might say that it extends a little beyond. She would record a length of 3.21 centimeters. The 1 is the estimated digit. Who is right? Both are. The last digit in a measurement is the estimated digit. That means it is uncertain. As long as the estimated digit makes sense, no one can say that it is wrong. How many significant digits does each of the measurements have? The answer is 3. Significant digits include all measured or certain digits plus one estimated or uncertain digit.
Here's a question for you. This string is 1 meter long. If I use it to measure the width of your classroom, and I measure 8 meters and an additional 1/4 of a meter, how should I report the length using significant digits? Write your answer down and show your teacher. If you wrote 8 1/4 meters, that is incorrect. Using fractions does not tell us which digit is estimated. For example, 1/3 is 0.333333, and you could repeat the 3 forever, because that is an infinite number of estimated digits. If you said 8.25 meters, that is incorrect as well. We are not sure about the 2/10, so we must stop there. Using 0.25 is estimating 2 digits, and we're allowed to estimate only 1. If you said either 8.2 meters or 8.3 meters, you are correct. You remembered that the last significant digit is the estimated one. Pat yourself on the back. Well, no one can say which is more correct, the 8.2 or the 8.3. We would have to use a different instrument to get a more certain answer.
Now it's your turn to do some measuring. You will be given a string that is 1 meter in length and has no marks on it. You will also be given a meter stick that is marked off in tenths of a meter. Make a table like this one and measure the objects listed. Remember to estimate only 1 digit. When you've finished, show the measurements to your teacher.